Viewers like you make this program possible. Support your local PBS station.
What's it take to make our modern world?
Oh, Doc! That's amazing!
I'm David Pogue. Join me on a high-speed chase through the elements and beyond.
Oh my God!
As we smash our way into the materials, molecules, and reactions
It's a really cool enzyme because it makes life on Earth possible.
that make the places we live, the bodies we live in, and the stuff we can't seem to live without.
The only thing between me and certain death is chemistry?
From killer snails
Just when you think you've heard of everything, nature will surprise you.
and exploding glass to the price a pepper-eating Pogue pays.
Gotta be some easier way to learn about molecules.
In this hour, we'll dig into the surprising ways different elements combine together and blow apart. Come for the chemistry, but stay for the bacon blowtorch.
The power of bacon!
Beyond the Elements Reactions, right now on Nova. Imagine that you're about to take your first shot in a game of pool. The break. But when the cue ball hits the other balls, they all turn into a rat. Or imagine you snap a pencil in two, and it becomes a flower and a fork. That's how weird and surprising some chemical reactions are. You can take something as dangerous as the element sodium, which explodes on contact with water, combine it with a lethal gas, the element chlorine, and end up with something utterly different. Sodium chloride, table salt for your fries. Transformative chemical reactions are everywhere. They're going on all the time. They put the bang in explosives
That's a reaction.
Round two.
and the heat in hot peppers.
What am I doing?
Learning how to harness them has given us some control over our world and maybe even helped to make us human. And few folks know more about chemical reactions
This is not normal fire.
than my old friend, Theo Gray. Today, I've come to his mad scientist lair in Illinois to find out more about one of the most powerful weapons in our reaction arsenal, fire.
Fire is a chemical reaction, plain and simple. It happens to be the most important chemical reaction ever, times 10, bar none. When you think about the importance of fire to human beings becoming who we are, it's kind of the start of civilization almost, discovering how to control this amazing thing. Feeds us, chases away the bears, it lights up the night. There's almost nothing you could name that's more important than fire.
So what is fire anyway? You may have learned this in school. To make fire, a kind of combustion, you need fuel plus heat plus oxygen. That formula is simple, but what's happening isn't.
And what's actually happening here, it's kind of subtle. The wood itself isn't really burning. You see the flames?
Yeah.
Right? Most of the reaction is happening up in the air above the wood because it needs to mix with air. Like there's no air in the wood. And what's happening is the heat of the flames here are breaking down and evaporating compounds in the wood, bringing them up into the air.
Those gases from the wood are complex molecules made mostly of hydrogen, carbon, and oxygen. When the rising gases enter the high temperature area of the flames, they're joined by oxygen from the air in a swirling cauldron of complicated reactions. The gases break down and their atoms rearrange. If the gases burn completely, they'll form water and carbon dioxide. More often, incomplete burning produces a variety of other molecules. Importantly for us, the reactions also release energy, the light you see and the heat you feel. And that, at its heart, is what happens in chemical reactions. The breaking and making of bonds and the shuffling around of atoms.
You take two different things, you smash them together, they rearrange themselves, and then you get something else comes out.
And one of the big-time players in the game is oxygen.
Everyone ready?
With enough heat, it reacts with just about anything, as Teo soon shows me in his barn. This powerful cutting tool is called a thermic lance. It uses pressurized oxygen fed through a metal rod. This one's made of iron. We don't normally think of iron as something that can burn, but when lit in the flow of oxygen, it does, generating so much heat that you can cut through a brick or concrete. Demolition crews use large thermic lances to slice up all sorts of big, unwieldy things, from bridges to ships to machinery. But does the rod that burns in the stream of oxygen need to be metal? I shudder to ask why you've got plates of bacon here.
Well, because bacon is the funniest thing that you can form into a tube and shoot oxygen through. Unfortunately, actual American-style bacon doesn't hold together well enough. We need the engineering grade. This is Italian prosciutto.
Teo has already baked some tubes of prosciutto. The next step is to wrap them in yet another piece to create one large hollow tube, which he hooks up to his oxygen tank.
Okay, so now what can we do with this? The same thing you do with any sort of thermic lance. You cut something with it. We're gonna cut steel, because why not?
Oh, you're gonna cut steel with bacon?
Yes, a steel baking pan.
Wow.
You just have to get it hot enough.
The power of bacon! That's amazing!
Yeah, I mean, that's a good amount of cutting there.
I've heard of steel-cut oatmeal for breakfast, but
Bacon cut steel?
gaining control over fire has had an immeasurable impact on human civilization. In fact, the most popular construction material in the world has its roots in one of the oldest pyrotechnologies, roasting a certain kind of rock. We know it as concrete. Modern concrete is a mixture of aggregate materials like sand, gravel, and crushed stone with a binder, these days, most often cement. And that's key, because people are always confusing concrete and cement. Cement is the glue. Concrete is the end product. Cement sidewalks? No, that's concrete. Cement trucks? They carry concrete. But cement is the key ingredient. And that's why I head to the Lafarge Holcim Cement Plant, the largest in the U.S., located outside St. Louis, Missouri.
We shoot rock every day.
My day with plant manager John Gates begins with a bang. Is it safe to go down there?
Not quite. How's that for you?
That's a reaction.
That's awesome, huh?
Do it again! Now that, my friends, is a lot of limestone.
It's a lot of rock.
Before long, this will be holding together America's buildings and sidewalks.
That's right. We're going to turn this limestone into cement.
But what exactly is limestone? It's mostly calcium carbonate, a compound that, as its name says, has two parts. There's a calcium atom that has given up two of its electrons, making it a positively charged ion, the other part is carbonate, made up of 3 oxygen atoms that are sharing electrons with a carbon atom. Sharing electrons is called covalent bonding. The 2 electrons from the calcium have joined the party, making the carbonate a negative ion. The positive calcium ion and the negative carbonate ion attract, forming, surprise, an ionic bond. From the quarry, the limestone rock gets gradually crushed down, along with some clay and other ingredients, into a fine powder called raw meal, in preparation to enter the centerpiece of this whole operation, a rotary kiln about 22 feet in diameter and about 100 yards long.
Big kiln, largest in the world.
Kiln, as in like an oven?
Correct. Gas temperatures inside the kiln right here is about 2,000 degrees Fahrenheit.
Just before it enters the kiln, the powdery raw meal is dropped down through the kiln's hot exhaust gases. By the time it reaches the bottom and the entrance to the kiln, the heat has transformed the calcium carbonate from the limestone into carbon dioxide gas and calcium oxide, also known as quicklime. Normally, the kiln rotates at a speed of about 4 times a minute,
And ordinarily, this whole thing would be turning.
but it was shut down for maintenance.
Oh man, the mouth of the dragon!
Giving us a chance to see it from the inside.
So the whole thing is turning.
The whole thing is turning over 4 revolutions a minute as the material comes down the kiln. There's a burner pipe with a flame right here inside the kiln. And heating the material to 2,600 degrees, and the flame temperature is about 3,000 degrees Fahrenheit.
At this point, it looks like dark baby powder.
At this point, it looks like lava.
Oh, it does?
Yes, it's red hot lava.
As the main ingredient, calcium oxide, journeys down the kiln, getting hotter and hotter, it reacts with the other ingredients in the raw meal, creating complex synthetic compounds. By the time the whole mix reaches the end, it has a new name.
Clinker.
This stuff is called clinker?
It's clinker.
You couldn't call it something dignified
Oh,
like
I didn't name it.
calcium carbonate or sulfur trioxide? Clinker?
Clinker. Coming out of the kiln process before it goes into the cooler.
And clinker just refers to that limestone brew that's been cooked.
Correct.
But it still isn't cement. In the final stage, they add a little more limestone and hydrated calcium sulfate, a common mineral known as gypsum.
Conveyor belts seem to really be a thing around here.
And the whole thing gets ground back down to a fine powder.
And here it is, at last. No more grinding, no more ingredients. This is the finished product.
This is cement.
This is cement from the virgin limestone bluffs of Missouri.
There it is.
This Lafarge Wholesome plant produces up to about 4.4 million tons of cement a year. But that's just a small percentage of the 97 million tons produced in the US, and the 4.5 billion tons produced internationally. Virtually all of it ends up in concrete, that mixture of cement, water, and rock that is second only to water as the most consumed resource on the planet. That comes at a price, though. A massive carbon footprint. In 2016, cement production emitted about 8% of the global total of greenhouse gases. Over half of that from the production of clinker. Proposed solutions to this problem range from using wood to build high-rises, like this 18-story one in Norway, to injecting CO2 back into concrete as it cures, like this company in New Jersey making pavers, and even growing cement using bacteria, though scaling up those ideas remains a challenge. Maybe the solution, or part of the solution, to greenhouse gas emissions and global warming will come from a breakthrough in chemistry. That may sound foolishly optimistic, but the discovery of a chemical reaction over 100 years ago changed the trajectory of humanity, though few know the story. At the start of the 20th century, farmlands like these didn't look so verdant. And with populations rising, scientists wondered whether, in the near future, there would be enough food. The problem was nitrogen. Animals need nitrogen to grow. So do plants. But before the 20th century, farmers mainly depended on compost and manure to supply it to their crops, essentially recycling nitrogen from dead plants and animals. But there was only so much nitrogen in that cycle. Eventually, the growing population would exceed the farmland's capacity to grow food, leading to mass starvation. But there was a solution in the air, literally. Our atmosphere is almost 80% nitrogen, but that doesn't do plants any direct good. That's because it's in the form of N2, two nitrogen atoms sharing in a triple bond. 3 electrons from each atom are fully shared between them, which, as Ed Kussler, a chemical engineer and professor emeritus at the University of Minnesota, explains, makes the nitrogen molecule one tough cookie. So the atmosphere is 78% nitrogen. Why can't the plants just take the nitrogen out of the air?
Because you can't break this little bastard in half. You take the nitrogen, you have to break this triple bond between the 2 nitrogen atoms. And it's almost the hardest bond, the most difficult bond that we know. Basically, it's almost inert.
So the scientific challenge was for someone to find a way to take that stubborn nitrogen molecule from the air and bust it apart to create something plants could use, to invent a synthetic fertilizer. Around 1910, German chemist Fritz Haber and his team found the answer, which they demonstrated using this tabletop machine. From nitrogen gas and hydrogen gas, he could produce NH3, ammonia, a fertilizer itself, and a starting point to produce others. German chemist Karl Bosch brought Haber's work to an industrial scale, which is why it's known as the Haber-Bosch process. Ed and his colleague Joe Franek show me their tabletop version. Joe, maybe you can show us a little more hands-on how the Haber-Bosch process works.
All right, we're going to put a quantity of nitrogen in this syringe. Then we're going to put 3 times that amount of hydrogen in this syringe. We're going to light our Bunsen burner, and we're going to pass that mixture of gases over what will be our hot catalyst, which is iron in this case, and that will facilitate the conversion of the nitrogen and hydrogen into ammonia.
Okay, so 1 syringe full of nitrogen and 3 times as much hydrogen, because the formula for ammonia is NH3.
There you go.
It all makes sense! Joe passes the mixture over some steel wool heated by a Bunsen burner. The steel wool acts as a catalyst, a material that helps a reaction along while not getting consumed by it. After 6 minutes, it's time to see if it worked.
So, we now have all of our gases, our unreacted nitrogen and hydrogen, and the ammonia we've produced in this 1 syringe. And what I'm going to do is flush all of these gases through our indicator tube. If we flush some ammonia through these yellow beads, they'll turn blue.
Bravo. I see blue! So how much ammonia do you think we got?
Well, our indicator on the tube says that we have just slightly less than 2 parts per million of ammonia.
2 parts per million? So out of every million molecules, we got 2 of ammonia? At room temperature, this process barely works. And even with our burner heating things up a bit, nitrogen gas is so inert, the reaction isn't much better. Part of the problem is that this equation is a 2-way street. Some reactions are one-way, irreversible. When you bake a cake, you can't unbake it. But the Haber-Bosch process, like many reactions, goes both ways at the same time. So while some of the nitrogen and hydrogen are forming ammonia, some of the ammonia is breaking down into nitrogen and hydrogen. The trick is to find the optimal conditions where that balance heads in the direction you want. One tool is pressure. Bosch's industrialized version compressed the gases to around 175 times normal atmospheric pressure. And that huge pressure cooker ran very hot, 550 degrees Celsius, around 1,000 degrees Fahrenheit. Enough to make the hydrogen and nitrogen react with the catalyst, but not so hot as to break up a lot of ammonia. Though the process requires extreme conditions, the discovery of a way to split apart that stubborn nitrogen molecule changed the world. It opened the door to the creation of artificial fertilizers. And it's hard to overstate the impact of the Haber-Bosch process on our ability to feed humanity. What were the lasting effects of this introduction?
2 billion more people. If you lose this chemical fertilizer, you lose 2 billion people. They starve. This is not a hypothetical issue. Haber-Bosch is the chemistry that you wish for because it's the chemistry that improves the amount of food that you can grow on our planet. And that makes an enormous difference to the stability, the health, the well-being of the people on the planet.
So one chemical reaction wound up radically changing humanity.
Yeah, some people argue it's the most important single chemical reaction.
Wow. But before you go out and hug your nearest ammonia-producing chemical plant, you may want to consider the downsides. Now that fertilizer is abundant, growers often apply too much. Runoff fertilizer has led to giant algae blooms and dead zones in oceans. Also, making ammonia uses a lot of fossil fuel. Annually, the industry as a whole accounts for 1% of global CO2 emissions. Ed Kussler is part of a team of scientists at the University of Minnesota working on a greener approach to producing ammonia. This is the industrial Haber-Bosch process in a smaller package.
This ammonia reactor here is making about 25 tons of ammonia a year. Standard commercial ammonia plant is making thousands of tons a day. So this is a much smaller scale.
It still depends on high temperature and pressure, but it's powered by nearby wind turbines. You're taking nitrogen out of the air, you're making hydrogen out of the water, you're making it out of nature.
Yep, right here in this room.
The long-term vision is that small facilities like this pilot plant could make enough green ammonia for a county's worth of farms. In this area, about 130,000 acres.
We are making fertilizer from air and water. It's just straight alchemy. You're not going to get rich doing it in the new green way, but you can sure make a difference in the way the planet is.
Scientists estimate that 50% of the nitrogen atoms in any person alive today, at one point, passed through the Haber-Bosch process. Yet Fritz Haber's legacy is mixed. He won the Nobel Prize in Chemistry for his discovery, but is also considered the father of chemical warfare, having proposed and supervised its use in World War I by the German army. Some historians believe that the Haber-Bosch process itself may have extended that war by years, because it gave Germany a new source of nitrogen compounds, key ingredients in explosives. What makes them key? It all goes back to that stubborn nitrogen molecule. Think of it like a spring. Pulling the atoms apart takes a lot of energy, and sticking them into nitrogen compounds keeps them separated. But in explosives, those compounds are designed to fall apart quickly, freeing the nitrogen atoms to spring back together and releasing the stored energy from pulling them apart.
Seems like a good place to blow stuff up without risking hitting anything.
Yeah, that's why we like having our surrounding mountains.
To better understand the role of nitrogen compounds in explosives, I've decided to return to see some old friends, the engineers and scientists at the Energetic Materials Research and Testing Center at New Mexico Tech. We've had some fun in the past.
This is the most fun tailgate you'll ever come to.
So let's see what Ordnance Tech Jonathan Merkel and chemist Tom Pleva have in store for me today. It's cotton? Cotton balls?
That's correct.
Like cotton balls?
Yep.
Now, you might think that cotton balls don't explode. And you'd be right.
That was underwhelming.
Cotton fiber is about 90% cellulose, a key structural component in green plants, composed of carbon, hydrogen, and oxygen, but no nitrogen. So our cotton balls will burn, eventually, though not explode.
The spores are erupting!
But back in the mid-1800s, chemists discovered that they could add to cellulose what are called nitro groups, each a nitrogen and 2 oxygen atoms. That turned it into nitrocellulose, also called gun cotton. Those nitro groups made something that burns like this into something that burns like this. Flash paper. But nitrocellulose is no joke. In a confined space like a gun barrel, it can be powerful. It was the propellant the military used to launch the shells out of these 16-inch guns on Iowa-class battleships. And it's still a propellant today in 155mm artillery. Our next test is 50 pounds of nitrocellulose propellant, the kind used in those large-bore guns.
We give you 50 pounds of gun cotton.
Since the sphere container isn't sealed, it won't explode.
Delivered unto the earth.
But what will happen? After Jonathan wires it up, we head to a nearby bunker to find out.
Here we go. 3, 2, 1.
Compared to plain cotton, this is a show. The burning nitrocellulose generates rapidly expanding gases, including carbon dioxide, carbon monoxide, water vapor, and of course, nitrogen.
It's pretty.
Packed behind a shell in the barrel of a gun, the pressure from the expanding gases would hurl the shell forward. In our open bowl, it's more like fireworks, with the gases sending burning pellets up in the air.
That's just a propellant. That's a low grade here. We're going to move on to actual explosives now.
Oh, yeah?
Yeah.
What's first up?
So we're going to start off with ANFO.
ANFO?
That is the biggest mining explosive that we have.
Oh, cool.
ANFO is an industrial explosive used in mining and construction. It accounts for about 80% of all the explosives used in North America. Probably no chemical shows better the intimate relationship between fertilizer and explosives. Though the name ANFO stands for ammonium nitrate and fuel oil, it's over 90% ammonium nitrate, the same stuff as synthetic fertilizer. Ammonium nitrate is built around nitrogen atoms, so it packs way more nitrogen than nitrocellulose. That means ammonium nitrate can be very dangerous. This is the aftermath of the deadliest industrial accident in U.S. history. The explosion of over 2,000 tons of ammonium nitrate aboard a ship in Texas City, Texas in 1947. In 2020, in Beirut, Lebanon, there was a similar explosion. A waterfront warehouse containing thousands of tons of ammonium nitrate caught fire and detonated. The blast killed over 200 people, injured thousands, and left an estimated 300,000 homeless. Our ANFO test will be just 50 pounds of the stuff.
50 pounds.
To get a reaction going, even one that will release a lot of bang, you need to put some energy into it first to get some of the bonds to break. That's called activation energy. This is nitrogen triiodide, an explosive whose existence is so precarious, minimal activation energy is needed. Even just the touch of a feather. In contrast, ANFO is hard to set off. So Jonathan hooks up a booster, a smaller explosive. Since much of Emertech's research and training involves explosions in human-occupied environments, they typically add a wooden dummy for scale and to demonstrate an explosive's effect.
You good? Okay, here we go. 3, 2, 1.
That, my friend, is a firecracker. That was like 7 stories.
So what just happened? Jonathan ignites the booster. That's the black smoke you see. The pressure wave from the exploding booster in turn detonates the ANFO, breaking the bonds holding the ANFO atoms together. They rearrange into more stable gases, nitrogen, carbon dioxide, and water vapor, along with some carbon monoxide and nitrogen oxides. The hot gases rapidly expand, creating a supersonic shock wave traveling at about 2 miles per second. If you look at just the nitrogen atoms of the ANFO, it's like the unhover process. Most of the nitrogens from the ammonium ions and nitrate ions reunite into their more stable preferred state, N2. In fact, about half of the power of the ANFO explosion comes from nitrogen atoms reforming into nitrogen molecules. Here we are, what, a quarter of a mile away? And you could feel the ground shaking.
Yep.
And that's 50 pounds.
That's only 50 pounds, yes.
Next up, you've seen it in movies. And you probably even know its name.
What's that? It's C4.
And just one look at its active ingredient should tell you we've upped our game. Cyclotrimethylene trinitramine, commonly known as RDX. While it has 3 nitro groups, there's even more nitrogen built into its ring. And even though the nitrogen triple bond is one of the strongest in nature, the single bonds between the nitrogen in the ring and the nitro groups are rather weak, often the first to fail when detonated. Oh my. Last one for the day for us.
Yeah, 50 pounds of C4.
All right. Should I be offended that they've dressed him like me? Is there a hidden message in that?
I wouldn't take it personal, but, you know.
All right.
Oh, wait, I gotta go do that.
Oh, but it looks so cool.
I know, Charging. Okay, here we go. 3, 2, 1.
When the detonation pressure wave hits the RDX molecule, the ring compresses and then flies apart. The atoms recombine into carbon monoxide, water vapor, and nitrogen gas. Those reactions produce far more heat than ANFO does, which makes the gases expand much more rapidly, giving RDX over twice the explosive power.
So we have more heat and energy in there.
There's more nitrogen in there.
Exactly.
Does that mean that the future is just all nitrogen?
That is the goal. We are trying to make entirely nitrogen-composed explosive molecules.
Here's one from the drawing boards with a great name, octaazocubane. Entirely made of nitrogen, it is predicted to have a faster velocity of detonation than any known non-nuclear explosive, if someone can just figure out how to make it.
I think that's all that's left.
And so ends our day of the un-Haber-Bosch process. Much of the nitrogen in our explosives has returned to its happy, or at least extremely inert state, as N2 molecules in the atmosphere over New Mexico. In chemistry, reactions tend to consume other ingredients, transforming them into something new. That's the process that chemical equations are designed to explain. But in biology, molecules can sometimes bind to each other without consuming or producing anything new. They can act as triggers or messengers. Or, as it's sometimes described, like a key fitting into a lock. To learn more about molecular locks and keys, I've come to experience them viscerally.
Oh, wow.
Here at the Burke's Pepper Jam in Bethel, Pennsylvania.
Smell that.
An annual festival of food, entertainment, and contests, all centered on chili peppers. Reaper Evil hot sauce. They do have an ambulance on hand, right?
They do.
When it comes to peppers, I'm a novice. But the first thing you need to know is that the black pepper you see sitting with salt and chili peppers have different chemistries and histories. Black pepper is the dried, ground-up fruit of a flowering vine native to Asia. Its kick comes mainly from the molecule piperine. While one side of the world had black pepper, the other side had chili peppers, first domesticated by Mesoamericans and then traded around the world by European explorers. The main active ingredient in chili peppers is the molecule capsaicin. More on that in a bit.
3, 2, 1, eat!
The jam features a pepper eating contest for kids, but they wouldn't let me in. So I plan on entering the one for adults, after I get some advice. I've actually never eaten a pepper by itself.
Bow out when you feel you should.
Really?
Raw pepper is a completely different deal. I can't do it.
You can't eat a Reaper? Is there any way I can prepare?
You got your will made out?
You don't have anything to do for the next 3 days, do you?
Yeah, you're gonna feel great Monday morning.
A big round of applause for Lizzie. Well done.
Time to put my tongue to the test.
Long hots. Red Fresno.
Here's how the contest works. There are 10 rounds of increasingly hot peppers.
Peach Copenhagen. Big Red Mama.
Their spiciness measured on a scale invented in 1912 by pharmacist Wilbur Scoville. It estimates the amount of capsaicin in each pepper. Contestants have to eat a pepper and then wait 2.5 minutes to allow the burn to grow. If they drink the milk in front of them, a popular way to douse a tongue on fire,
They are eliminated.
they're out. My competitors include some rugged-looking characters. And Leah,
I've never done this before. I figured this out 2 hours ago.
a 15-year-old who entered with the permission of her parents.
We begin our contest with the long hots. Let's turn up the heat. Eat!
And we're off. Zesty, with just a hint of poison.
Round 2, we're gonna start with the red Fresno pepper. Eat, 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 eat.
Gotta be some easier way to learn about molecule.
All right, are we ready? Eat!
That was not designed for human consumption.
Round number 4, habanero peppers.
Parts of my body I didn't know I had are on fire.
10 more seconds. You got this.
I can't.
Don't do it. No! The orange Copenhagen pepper.
What am I doing? Oh, man. Oh, my God.
Don't do it.
I want it! Wherever you are, Scoville, I hope you rot. Cheers!
No!
So, I'm the first to fall. Is there a porta potty? But there's a bigger mystery. How does a pepper's capsaicin convince my mouth it's on fire? Not recommended. I think I'll find the answer here at Penn State University's Department of Food Science.
We all study food, so you have psychologists and microbiologists and engineers.
I'm here to see John Hayes. He knows a thing or two about the active ingredients in these.
So when you went and tasted them, what did you experience?
Oh man, my gut twisted, my tongue burned, my flesh burned, I cried, I got red, my nose ran. It's like putting your tongue on the stove and leaving it there.
That was an aversive response. This plant has evolved a chemical called capsaicin. And the reason it makes that is to keep animals from eating the chili pepper.
Oh man, the Chili Festival people never got that message. And we're just a really stupid species.
Exactly. We're one of the only species that learns to like that sensation.
Ultimately, pepper plants are playing a pretty good trick on humans as well. Capsaicin really is a key ingredient. It has a long, spindly tail attached to a ring.
That ring end fits into a specific receptor that's expressed all over your body.
Not just our tongue.
Not just your tongue.
Oh, man.
This receptor, this lock, is actually a heat pain sensor.
Normally, the receptor, called TRPV1, activates when it comes in contact with something over 106 degrees. The result is a pain message to the brain. Ouch! Something's hot!
It's a warning signal to tell your body danger.
And here's the tricky part. When you eat peppers, those capsaicin keys fit into the heat pain receptors in your mouth, altering their sensitivity.
And so what the capsaicin does is it fits into this molecular thermometer and it lowers the temperature at which it activates it.
Like a changed thermostat, they now activate at body temperature, sending a false signal that's identical to the one your brain would receive if you ate something literally burning hot. It lowers the temperature at which we feel burning pain.
Yes.
But it's not actually burning us?
Correct.
It's not. I'm not going to see scar tissue.
No.
No matter how hot it is. It's all a fake out?
Absolutely.
Up next, the yellow 7-pot pepper.
Back in Bethel, the pepper eating contest is entering its final rounds.
That one's warm.
Oh, it's burning now. I'm trying to think of a happy place. I can't find one.
Evidence that capsaicin's working on the molecular locks of everyone's heat pain sensors is easy to see. As they eat a big red mama rated at over 1 million Scoville heat units.
Don't tap out now! Don't tap out!
One more falls. We're down to the final 4.
I'm ready to leave. I can't abuse these people anymore.
This time, the organizer adds concentrated pepper extract. How long can this go on? Then, suddenly, a resolution that no one saw coming.
Oh! Way to beat him! Big round of applause! Big round of applause!
Leah, I am not worthy. You rock! What does a woman with that kind of fortitude and strength want to be when she grows up?
A fighter pilot.
Why am I not surprised? Ultimately, the capsaicin molecule is an illusionist, able to trick my nervous system into thinking my mouth is on fire. But what about the molecules that pose real danger? Molecules designed by nature to kill. Time to meet my first professor of venoms, Mandy Holford of Hunter College. Now, I couldn't help noticing there's a huge, terrifying tarantula on me. Is she poisonous?
No, she's not poisonous.
Oh,
She is, however, venomous and could still be lethal.
thanks for bringing that up. Poisonous and venomous don't mean the same thing?
No, not at all.
Poisonous versus venomous. It all comes down to the delivery system. If you bite it and get sick, it's poisonous. But if it bites you and you get sick, it's venomous. In general, the source of their toxins is different as well. This poison dart frog becomes poisonous from its diet. If raised in captivity on different foods, it can become non-toxic. Whereas this rattlesnake generates its own venom. It's built into its DNA. So, snakes, scorpions, spiders. Which fearsome creature is the focus of Mandy's work? Killer snails? Is it accurate to say that you study killer snails?
Killer snails are actually my affectionate term for venomous marine snails. And so these are snails that live in the sea and they have a venom like snakes or scorpions or spiders. And the venom can be very lethal to humans.
It's true that the snail can kill you, but usually it's just looking for dinner, a worm or a fish. So I'm a fish. What happens to me?
Well, what happens is this guy will smell that you're in the water, right? He puts out something called siphon, and it's a chemosensory organ. Smells that, tasty meal in the water. Then it sticks out something like a tongue. It's called a false tongue, proboscis. And on the tip of the tongue, it has a little tooth filled with venom that then will get injected into the fish. Fish instantly will become paralyzed, depending on what cocktail of venom gets injected to it. The snail will then open its mouth really wide, swallow the fish whole, and have a really nice, tasty meal.
The whole thing sounds so improbable.
I love it. Just when you think you've heard of everything, nature will surprise you with something new.
So what's in that paralyzing venom? To find out, Mandy and her team collect specimens from around the world. Back at the lab, they analyze tissue samples from the snail's muscular foot and its venom gland.
So we're eventually going to look at the DNA so we can make a species identification, and that we can use the foot tissue for. And then the venom gland tissue we can use to look for the individual venom toxins within the venom duct.
Turns out the cone snail's venom isn't one thing, but a cocktail of as many as 250 short mini proteins, also called peptides.
So if you think of venom, think of it not as like a single bullet, right? It's more like, I like to describe it as a cluster bomb. It's a series of bullets coming at you, and each individual bullet has a target in the physiological system.
Each venom peptide has evolved to mount a very specific attack, often acting as keys that fit a cell's lock-like receptors. In the case of the nervous system, that can prevent a specific neuron from transmitting an impulse. Or, conversely, jam the neuron open, generating a flood of signals. In the wild, all those targeted attacks paralyze the snail's prey. But the precision with which the venom peptides act also means that they may have another role, as medicines.
And so we study these venoms to try to figure out novel medicines for treating things in pain and cancer. Actually, they make great drugs because they're highly specific, very fast-acting, and very potent.
A venom curing instead of killing? Wouldn't be the first time. There are currently at least 7 drugs on the market developed out of the study of venoms. They include an anticoagulant derived from medicinal leeches and a diabetes medicine from Gila monsters. There's even one already from cone snails, an analgesic to treat severe chronic pain.
And it's the exact peptide that you would find in the venom. It's not a derivative of it. It's not a small molecule. It's exactly as nature expressed it in the animal.
And I'll just run a simple DNA extraction.
Mandy's team has already made some major breakthroughs.
I could do nano LCMS and see what's inside of here.
In 2014, they identified a peptide from another venomous snail that attacks liver tumor cells, inhibiting their growth. It's cutting-edge work that's reaping the rewards to be found at the intersection of chemistry and biology.
Learning how the venom is used more in ecological settings helps to further us in terms of how we understand how it can be applied for medicinal or therapeutic applications. And so right now it's a fun time to be a venom scientist because those worlds are colliding.
In both chemistry and biology, change is a story told through reactions. And understanding those reactions has given us new insights into both our world and ourselves.
If you lose this chemical reaction, 2 billion people starve. This is not a hypothetical issue.
And with that comes a lesson. Oh, man! Just as a molecule can act as both a venom and a medicine, or one reaction can both help feed the world and blow it to bits, our scientific knowledge is a powerful tool.
The power of bacon!
But it's up to us to learn how to use it well as we continue to go beyond the elements.